Hello guys, on today's video tutorial we are going to do a thermal simulation on this wonderful teapot. I have just imported the CAD models, which consist of two parts, teapot 1 and teapot 2. Teapot 2 is the cap of this teapot, and I have made myself this design. I hope you like it, and let's go. You can easily create our instance by including both parts, since they have been designed the same coordinate systems. No need to rotate or translate, it's already ready. Let's create our material, which will be porcelain, and for the steady state analysis we only need thermal conductivity. Let me check my notes. 0, 15, perfect. And let's create the relevant section and easily assign on the part. Color becomes green, the same for the other part. Perfect. So let's move to the mesh. Okay, as you can see, the color is orange. This means that we can also mesh it with tetrahedral elements. Now it's pink, perfect. It's because, okay, the geometry it's a little bit complex and it will be very challenging to make it with hex element. So let's go with tetrahedral elements. Select heat transfer, quadratic, this is the name of the element, 10 node quadratic heat transfer tetrahedron, perfect. Click here for the approximate global size. Let's make it 2 for the beginning. Let's see. Okay, let's mess it. Okay, can be better, but leave it as is per now. Let's go to the main part. The same, the geometry is complex, tetrahedron elements. Select heat transfer, same name, global size the same, and mesh the part. Okay, I don't like here the elements, these elements, but let's continue and see it next. So now we're going to create the time step of the analysis and select a heat transfer analysis. We're going to do a steady state analysis. Maybe in the next video we'll try a transient one and explain the differences between these two analyses. The field output request has been created automatically, and let's move down the model tree, and now we meet the interaction module here, and let's create for the including the convection with the ambient air. Abaqus has this tool surface film condition that we can select, and select the outer surfaces that will be in contact with the ambient air. Hold the shift key and select all the surface that we need. The same for the cap. Perfect. And we can also select this surface. Let's leave the bottom surface. So this is the two parameters that we have to include. The sink temperature, the ambient air, let's say 20 degrees of Celsius, and the film coefficient. As we have said in a previous video, for natural convection of the still air, I used this value, working in millimeters here in Abaqus, 0.5. Perfect. So since we have two parts, the cap and the base, we have to create the conductivity, the conduction between these two parts. So having the interaction properties, select thermal conductance, values of the units, and here now we have to create the contact pair surface to surface. Let's hide instances the cap for the time for now, and X surface to surface, perfect. Select these surfaces for the contact and return it back. Let's click this button for a section view and we can select this surface for the contact. Perfect. Here is the property that we created previously. Click OK. Now we're done. Perfect. Let's move on. For the boundary condition, let's assume that we have here a liquid of water of T at a temperature of close to 100 degrees. Let's hold the shift key and select this surface and click done, and okay, let's make it 90. Perfect. Also, let's create a predefined field in the initial step of temperature at 20. Okay, maybe it's not necessary, but not bad. Okay, let's try to make first job. Teapot steady A. Teapot. Select the processor. If you want more, no problem. You have more. Click yes. Maybe it will take some minutes. Okay, the analysis has been completed. Right-click results. Let's click this button to show the contours, and here we select NT11 for the temperature. Oh, something goes wrong. Okay, guys, let's go back, and we made a mistake here in the interaction. Okay, here, this is the mistake. The ambient temperature is 20 and not 200. Let's click it again, submit the job. Okay, guys, the analysis has been completed again. Let's check the results. NT11, okay, now it seems that it's correct. So we can click this button for the section, and okay, here we see the contours that the conduction to the cap has worked, it's valid. And if you click this button, tools, query, nodes, values, here nodes, you can see it in the outer wall of the teapot. We meet 26, we see 26, 26.2, here 24, 25 with the internal 90 degrees. Okay, in the bottom we see 89. So we could include some part of the table, since this teapot is supposed to lay on the table. So a small amount of energy could be conducted to the material of the table, but Let's go back and make another trick. We can use this load boundary condition, and let's assume that a small amount of heat flux is exerted from, let's make it as it is, from the bottom phase. Right click and again submit the job. Yes. Okay, analysis has been completed again. Right click, results. You can see the temperature. Okay, so you can see the difference now. Let's again click carry. Okay, the temperature on the wall remained the same here, 26.2.1, here 25, and now here on the bottom we see values 90 here, but the bottom phase around 70, maybe it's more close to the reality. Perfect. Okay, let's go back and try one more thing. Let's assume that this teapot is made of metal, of steel. I forgot to mention that the design, I have designed this part with a thickness of 3 millimeters here on the walls. Maybe it's not a real case for a metal one, but let's try it to see the difference. Stainless. So let me check also my notes. Okay, the thermal conductivity. Create the relevant section. Stainless. And let's go under the part and turn the porcelain edit to stainless for this part and this part as well. Very easily, without changing any other parameters, any other settings, create a second job, teapot, steady B. 2 processors, and let's submit it. Yes. Perfect. The analysis has been completed. See the results. Click. Oh, and now we can see the difference. Here, the levels of the temperature on the outer wall is about 54.7, 53, almost the double from the porcelain. Also, we can see the conductance here, conductivity, and here the difference is smaller. But here, the average temperature is almost twice the previous than in the previous analysis. So guys, this is for me now. Hit subscribe if you like my video, and stay tuned for next videos. Thank you for watching.